Dimensional analysis is a simple but very important skill that will allow you to ensure that the equations you are using are definitely correct. But what does it mean? Dimensional analysis comes from a fundamental rule in writing equations that the dimensions, or units if you prefer, of every term in an equation separated by a plus sign, a minus sign, or an equals sign should agree. So if you have an equation for velocity, then velocity is known as distance over time. So every term separated by a plus, minus, or equals should agree with distance over time. Taking the example of Suvat, we have v equals u plus at, where v is your final velocity, u is your initial velocity, a is your constant acceleration, and t is the time taken. Then we have distance over time here for velocity, as we've defined. U is the initial velocity, which again is distance over time. We have A, which is the change in velocity per unit time, so that will be distance over time squared, and we have that multiplied by time. So as you can see, obviously distance over time is agreed upon with v and u, and with at we have that the t's cancel and we are left with distance over time, and therefore this is a valid equation. So what this basically allows you to do is to confirm that the equation you have written is actually dimensionally correct and is valid. So it just allows you to very quickly check on the fly whether you've remembered your equation correctly. So let's look at an example where we actually use it to remember the correct equation. Here we have a circle that has a radius given by capital R, and we remember these two equations, pi r squared and 2 pi r, but we can't remember whether they refer to the area of the circle or the circumference of the circle. Well, using dimensional analysis, we can come to the conclusion that pi r squared has dimensions of area, because we have pi, which is dimensionless. It's simply a number. It doesn't have any dimensions. It isn't measured using any measurable quantity, like meters or or Kelvin for temperature or anything like that. But then we have r, which is a distance, and it is squared. So r squared, a distance squared, means an area, as you would find the area of a square just by multiplying the length of its two differing sides. And then we have 2 pi r. Again, 2 and pi are both dimensionless, whereas r has a distance of length. So we know it must refer to length. So from here we've managed to figure out that pi r squared must be referring to the area and 2 pi r must be referring to the circumference. Now obviously this only applies to whether you can actually remember these two equations in the first place, but it's actually quite a helpful skill to be able to just quickly check in your head whether you've remembered it correctly, because all of these equations are quite similar, especially with the properties of circles. So it's quite easy to mix them up. It's a useful skill to be able to just look at an equation and go, right, that is definitely for an area, and because I know this has to do with circles, it's probably going to be the area inside the circle, and likewise for the circumference. So now I'm going to look at another example using the Suvat equations, a list of equations that describe the motion of an object that is accelerating at a constant rate. So we have an equation for the distance travelled of an object given its initial speed and its acceleration and the time it has taken to do this. And so we kind of remember it as s equals ut plus half at. But we're not entirely sure whether this is right. We may think we've actually remembered it slightly wrong. So let's dimensionally analyse it. We have s, which refers to the distance travelled, so that is a distance. We have u, which is its initial velocity, so that is a distance over time. Then we have t, which is the time taken, and so that is a time. We then have, separated by a plus, sine half AT. Half is just dimensionless, it is simply a number. A refers to distance over time squared, because it is the rate of change of velocity with respect to time. I just need to put a squared there. And t, again, is time. So we now cancel the terms that we can, and we have distance is equal to a distance plus distance over time, which is a velocity. So that isn't correct. So now we know that if the first two terms agree with each other, the third term must also agree with them. So we posit that maybe we need an extra factor of time to cancel out the time on the bottom there. So instead we think, what if the equation is S equals ut plus half AT squared? And actually it turns out that is the correct equation. Now, again, obviously this doesn't give you the complete description of everything. You can't just use dimensional analysis to instantly remember what every single equation is, but it is a simple little skill that helps you to more consistently remember and actually just be able to check independently that the equations you're using are definitely correct. Suvat equations, there are many of them, and they're quite easy to mix up. They've all got very similar terms, and you know, it's perfectly understandable if you were to miss out a factor of t. So it's just good to be able to check whether you've actually done it correctly. The great thing about dimensional analysis is that there aren't actually many dimensions to remember. We're able to describe all quantities in the universe using only a few fundamental qualities. We have length, time, temperature, mass, and charge, as in electrical charge. Now, these are all given their own symbol, and what we use is square brackets with a letter to denote what we are referring to. So for length, that is square brackets with an L. Time, it is square brackets with a capital T. Temperature is square brackets with the Greek letter theta. Mass is square brackets with M, and charge square brackets with Q. So quite easy to remember. They all, you know, it's all pretty intuitive. The only one I'd say is quite unintuitive is theta, but to be fair, in Greek, theta actually refers to the letter T. So, you know, not quite as bad as it seems. Now, here I've demonstrated how you can actually express a couple of quantities just by using all of these fundamental dimensions. So we have force is equal to mass times acceleration. That is the fundamental description of force. So from that, we can say that if mass is obviously described by the dimension of mass and acceleration is length over time squared, then force is just ml over t squared. And similar with density, its description is mass divided by volume. So if volume is just, well, all you need to do is think about what is the volume of, say, a cube. It could be the volume of everything, but the cube is the most simple thing. The volume of a cube is just the length of one side cubed. So its dimensions should be L cubed. And so rho is described by mass over length cubed. Now, what you need to do, if you have a more complicated equation, is think, right, what is this describing? Is it an equation, say, for force? So you have the gravitational force, which is F is equal to G m little m, where m and little m are the masses of the two objects that are gravitationally attracting each other, over r squared. So all force is the same force, so they should all have the same dimensions. So we should expect the term on the right hand side here, gmm over r squared, to have dimensions of ml over time squared. And that means we can actually find out what the dimensions of g are. Now, to be honest, I don't remember off the top of my head what the dimensions of g are, but actually if you're in if you're in an exam, then you will actually be given the value of g, because you're not really expected to remember to remember that stuff. So actually, if you go and look at the value of g, then you notice that it also gives you its units. And so by looking at those units, you can actually determine what its dimensions are. And then, if in an exam you suddenly can't remember the difference between the acceleration due to gravitational force or the force itself, then you can actually work out what the expression should be, that it should cancel out such that you have force is equal to ml over time squared, if that makes sense. Now here I'm going to highlight a very important point, and that with certain functions it is absolutely paramount that the argument inside those functions, so here x, should be dimensionless. So it should have no dimensions, it should simply be a number. Because in the case of cos, sine and tan, inside those arguments are actually meant to be angles, and angles are dimensionless. This is very important because you can have equations that have cos with some long expression inside it. And so you can actually confirm to yourself whether it is correct by checking whether the argument is dimensionless. Similarly to e to the power of x, all exponents should be dimensionless. So even if I had written 2 to the power of x, that x should still be dimensionless. And so this is an extra way that you can confirm to yourself whether you have the correct equation. So, as you can see, dimensional analysis is a potentially very powerful tool. It cannot help you solve everything, but if you become comfortable enough with it, you can use it very quickly to check your logic and ensure that all the equations you're using are actually correct. To test yourself on this skill, I've included a few multi-choice questions in the supplementary notes below. Hopefully you found this useful. It might seem, I don't know, kind of pointless at first, like why go to all this effort to do this, but actually if you teach yourself to do it almost subconsciously, then you can just very quickly independently check that what you're doing is correct. Even what your teachers are doing are correct. I've had many cases before where a teacher has just written an equation up on the board, and using dimensional analysis I've been able to recognise that they have actually remembered it wrong and brought them up on it, and they've realised and then changed it to what it actually should be. Everybody makes mistakes, and this is just a good way of making sure you don't make any.